Hello, everybody. In this notebook, we are going to cover the process of fine-tuning a pre-trained model for image classification. In the previous notebook, we learned about transfer learning, and fine-tuning is a very similar concept. It is just, transfer learning taken to slightly higher level. So just a quick refresher, if you remember from the previous notebook, typically image classifiers, they have this sort of an architecture. You have an input layer, and then we have feature extractors which extract useful features from the image. And then there is a classifier layer, a few classifier, this acts like a bank. The whole thing acts like a classifier, but there are several layers in it. And this one is usually fully connected, and these ones are convolutional layers. In transfer learning, we learned that you could actually add to this layer, or you could unfreeze this classifier. You basically modify this classifier somehow and keep all these feature extractor portion completely frozen, right? And usually you would use transfer learning when you do not have enough data. Then you do not have enough data to train the entire network. So you would say that, okay, the feature extracted on a different data set is also fine, okay? And I'm just going to worry about the classifier part. But if you have more data, right, and especially if you think that your data set is very different from, let's say, ImageNet, then you would want to train a few more, a little bit more from the classifier also. So you train the classifier and a few layers of the feature extractor. Sorry, I misspoke in the previous line. So here is what the diagram looks like. You could use a pre-trained model without changing anything, and you'll be able to classify the 1,000 classes that ImageNet has. But you could also, if you have a lot of data and for some reason you want to train the entire network from scratch, you can start from completely random weights and train the entire network. This almost is never done unless you are working at a company like Google or Facebook where you're trying out a new model architecture. You typically would not try to train a new, from scratch. Then we have transfer learning where you only modify the classifier piece, okay? And then finally we have fine tuning where you modify the classifier as well as part of the feature extractor. All right, so we'll see how it is done. And for this, we are going to use MobileNet v3. This is a small architecture, very useful when you're using on edge devices. And we are going to use this 10 monkey species data set. You can look at this data set on Kaggle. And there are basically 10 monkeys in this data set. The size of the image is 400 by 300 pixels. And the labels, I cannot even pronounce some of these names. But these are the names of the different species. We'll just call them N0 to N1. Okay. Johnny. All right. Now we are going to use, Torch Vision has some pre-trained models, including MobileNet v3. We are going to get it from there, and then we are going to fine tune it. And this notebook is going to describe how it is done. First, we start with, our standard Torch Vision, Torch info. This is not part of Colab usually, so we install it. And then we install a bunch of libraries. These are I've gone over these imports so many times that I'll skip it for this notebook, but these are standard imports that we have seen many times. Similarly, we set the seed, and as you remember, the random seed is set so that the random number generators at various parts of the code, they are set to some fixed value, so that when you run this code over and over again, you get the same output. All right. Then we get this monkey data set. We have downloaded it, and you can just use wget to get it, and then we unzip to get the the monkey data set. Next, we are creating a class of training config. These notebooks, we have tried to make it slightly differently based on how people generally use. One of the ways is to create this configuration class for training, and it has the standard things like batch size. We are setting it to 32. Number of epochs, we are setting it to 20. Learning rate, we are setting it to 10 to the power minus 4, and then so on and so forth, right? So next we create an instance of this class, training config, and then we check what is the device we are running on. If it is CUDA, then we say that, okay, this is available, and then we just print that CUDA is available. That is what we want. Otherwise, the training can take some time. All right, and then we are just listing, what are the various, which I just showed, what are the labels, N0 to N9, and these are the scientific names of these monkeys. The folder structure, if you look inside the folder structure, it has a root, then we have training and validation. There are 2 folders. Inside training, there are 9 subfolders which contain the images, and similarly inside validation, we have 9 subfolders or 10 subfolders that contain the 10 classes. So here we are basically saying that the root directory is this one, which we just downloaded, and then we are concatenating training. As you can see here, training. I don't know why it's training, but that's how it is. And similarly, the validation root is monkey_species validation. Then we are going to use, there are labels. There's a text file called monkey_labels.txt. And whenever, in data science, whenever we want to use, we are working with text files that contain these kinds of tabular data, or when we are using comma separated value files, we basically use pandas. So this we had imported right here, pandas as PD, okay? And this is really easy to use. It's very widely used. It can work with very large data sets. So basically we load this, CSV file, the labels file, and this just specifies that, okay, the text file is actually a CSV file, and the separator is a comma, and we load the CSV file into df, okay? This variable called df, and df stands for data frame. All right, so now df.columns, we are going to say these are labels, Latin names, common names, train images, and validation images. The reason we basically know these are the columns. And for Latin names, we are going to replace some tabs with spaces. It is just for cleaning up for display purposes, okay? So once we have done that, we can actually display the entire data frame. And you can see that the labels go from N0 to N9. We have the Latin names, we have the common names, we have the number of training images, the number of validation images for each category. Next, we need to do data processing. We know the mean of this data set. We are not calculating it explicitly here, but we have pre-calculated it, or we know it from Kaggle that this is the mean of the data set. And then we have the standard deviation, which is this for the 3 colors. We are going to resize the image to 224 by 224. Now, remember the image was 400 by 300. And you may be saying, okay, it is nonlinear. It's not scaled equally in both directions, and that's fine. It doesn't make much of a difference because the original size is not completely out of, it is 400 by 300. So it's not too bad. Next, we are saying that, okay, we need some transforms. We are going to resize the image to the size. Anti-aliasing is true. When you set anti-aliasing to true, it takes slightly longer time, but the quality is higher. And then we convert the image to tensor. All right. So this is standard. We have seen it many times. We also define, so this is pre-processing. We are going to do it for all all of them. Then we also define some common transforms, which is basically we are going to pre-process it and we are going to normalize it using mean and standard deviation. We also have a different set for training. So this is common transforms. This is what we are going to use for the validation set. For the training set, we are going to use it slightly different ones. We are going to use the pre-process, which is right here, the resizing. But we are also going to, during training, we want to augment the data, which means that we want to make more data from existing data. How can we do that? We can horizontally flip the data randomly. So that is one thing. We are going to do random erasing. So it randomly erases part of the data. And the reason this thing is helpful is that you're training the neural network to recognize even when part of the data is not available. And we'll see an example in just a moment. We are also applying random affine transforms. So affine transform, think about it as rotation, translation, scale, and shear. Okay. So it says that the degree of rotation rotated by 30 to 70 degrees, right? Randomly. Translate it by 10% to 30%. Translate means move the image by 10% to 30%. Scale it by 50% to 75%. And there's another one called, and we are also saying that you do this with probability 0.1, which means that 10% of the time, apply this random transform to it. And then finally, you normalize the image by mean and standard deviation. Subtract the mean and divide by the standard deviation. Now, during training, the more difficult you make the data set, the more you can see that suddenly the data set that you're using during this training, it has expanded. Earlier, you just had, let's say you had 100 images in the data set. By applying these random transforms from the same data, you have created a much diverse set of data, and the quality of the data has gone up, right? Because in every training set, in every training run, you are actually using slightly different variations of the data, right? And these are all valid. If you flip the monkey, the image of the monkey, it is still a monkey, right? The reason these data augmentations work is that even after doing these augmentations, the label doesn't change, right? And that is why you have artificially increased the variety in the data without doing additional work, right? We didn't have to do additional labeling. The label remains the same. We are just changing the data. So that's the goal of these transforms. All right. Now we have a data loader that is already part of Pytorch, which we are going to use. This is basically, you can use image folder. You can use an entire image folder, and it is going to load all the data from the image folder. So basically datasets.image folder, we are going to give it the root, which is the train root. And we are going to say that apply these transforms while loading the data. Similarly, we have val data, and we are going to create this data set from this image folder, which is val root. And then we are going to apply some common transforms, and we are ready. Okay. And if you want to check what are the classes, we can see that these are the various classes, right? And if you want to change these classes to IDs, 0 through 9. The length of the training data is 1097. Those are the total number of images. You can see here in this example, you can see that the summary is 1371 files, and out of these, there are 1097 training images, and the rest are test images. All right, so now we have the data set. We are going to create a data loader, and the data loader, basically this syntax we have seen before. We have to give it the data set. We are going to say that when you load, you shuffle, and then we also have to give it the batch size, because it's going to load a batch of images. And then the number of workers, it's okay to leave it based on the config. We can just say that, okay, we are going to load 5 workers. Sometimes the machine may not be powerful enough, reduce the number of workers to, let's say, 2, but right now the default is 5. The same thing we do with the validation loader, right? So just to reiterate, by now you probably know this already, that the job of the data loader is to give you a small batch from the data set, right? With these characters. You may say that, oh, shuffle it and then give me one batch, right? And we are going to, during the training process, we don't process all the data at once. We train small batches like 32 images or 64 images because first of all, it is a good thing to do. I don't want to get into the technicality of it. Even if you had a GPU with infinite memory, you would actually prefer to use small batches like this. The second thing is the GPU memory, right? If you're working with millions of images, the entire thing will not fit in a GPU memory. So that's why we have this data loader, which allows us to load the data very efficiently, and it gives us a batch of images. The mapping we have already seen, 0 through 9. So I'm not going to, actually this mapping is slightly different. The images that we had, the classes that we had seen before, these were the Latin names, right? We are looking at the common names in the mapping. So it's actually much easier to look at this, right? I think these are scientific names, but it says Latin names, that's fine. So, okay, now we are ready to display some images. We are using matplotlib, and we are going to visualize some of these images. Nothing special here. We are just getting, images and labels from the data loader, right? This visualization, visualize underscore images, it takes a data loader, and from the data loader, it says, okay, get 20 images, num images, and we are going to display those images. And nothing very special going on. It's very standard code. You basically go over the number of images, decide how many, the number of rows is fixed, 4, and based on that, how many columns you have to display, and then you just go over and get the images, right? So here we got all the images. The one thing you may notice here is that it says permute. When we use Pytorch, this is how the image is stored, channel, height, and width, but we want to make it height, width, and channel for display purposes. And that is what is going on here. Other than that, the code is pretty standard. Okay, so you can see, when we load it from the data loader, sometimes we have these black patches. Sometimes the images are rotated, but we also have these black patches. This looks funny. The black patch is randomly generated to make the training process harder, to add variety. And you can see this is random erasing with probability 40%. So 40% of the data actually has these black things, right? So that it can identify. If you have these things in the training set, it means that even if that piece is missing in the final image, in the test images, you will be able to identify it. So the training becomes more robust because lesser information is being given to it, and it is still trying to learn. So, okay, so you can see here we have rotation, translation. So it's rotated and moved, right? So it's rotation plus translation and scaled also. The image is slightly smaller. So this is what is called data augmentation, where we are applying all these transforms to the image so as to create a more richer data set. Next, we are going to load our model, the pre-trained model. From Torch Vision, we are getting MobileNet v3_small. This is a very efficient model and often used for edge devices, including phones. So here we are loading the model with the default weights. And first we are going to see, how many layers are there, feature layers are there, and how many classifier layers are there. As you can remember from this image, we have this feature extractor. We want to see how many layers are there. And there is this classifier, how many layers are there in this one. So when we do this, when we run this code, you will see that the number of feature layers is 13 and the number of classifier layers is 4. So out of the 13, we are going to keep the first 10 layers, and we are going to just fine tune the next 4. So here we are saying that when you load a model, all the layers are trainable, right? And to freeze certain layers, we have to explicitly say that, okay, required grad equals false, right? That way the layer gets frozen. So that is the first thing we did. We are going to freeze some of the classifier, some of the feature extraction layers. Next, we are going to look at what is the final, the shape of the final classifier. So if you do this, you'll see that it's a linear classifier, which means that it is a fully connected layer. The input features is 1024 and the output features is 1000. Now, 1024 is, 1000 is here because the number of classes it was trained on, ImageNet, is 1000, right? And the bias equals true here means that the neurons have weights as well as biases. So here we are going to replace this final layer with a different one. So we are going to keep the input the same. Only the output is going to change, and we are going to set it to 10 because this is the number of classes we have, and everything else remains the same. It's exactly the same. So instead of 1000 outputs, we are going to get 10 outputs. So now if you print it, you can see that the final output is this one, the new one. Okay. So now we are going to set our model to this model. We are going to specify the optimizer. We are going to use the Atom optimizer. As we had seen in the previous notebook, we had used the stochastic gradient descent optimizer. Here we are going to use Atom. Atom is probably the most popular one for image classification. And I cannot go into the details of what this optimizer does. We do cover it in our course, Deep Learning with Pytorch. But the basic idea of any optimizer is that after the gradients have been calculated, it uses those gradients to update the weights. And how the weights are updated is determined by the kind of optimizer. Next, we are going to set our device to CUDA if it is available. The log directory is set to this one, and then we also have something called a summary writer. So this summary writer is going to use the log directory as for input. This is where it is going to store the summary as well. And as always, we have seen in the previous notebook also, we can get a summary of this network by putting in the model and the input, a dummy input. And here the dummy input is basically an image of, this size. And we are getting this output. So the only thing to keep in mind here is look at this one. It says that it takes one input image and outputs a 10 class classifier, like 10 classes. So that's the details of this particular network. It's not important. It uses, as you can see here, anything under this features is the feature part, and then we have the classifier part, right? So that's something you can look at. One other thing is that there are these many trainable parameters. Others we have frozen. We have frozen these many parameters. Now, one thing you may notice is that, we had frozen a lot. We had frozen like 10 layers. Why does the number of parameters look so small, right? Which are non-trainable. The thing is that the convolutional layers, they are very sparse. They don't take as many parameters. The fully connected layers, on the other hand, that's where most of the parameters are, right? So that's why for images, when we move to convolutional layers, it made the networks really small and very efficient. So that's the beauty of convolutional layers. All right, so with that, we can start our model training and evaluation. We have this function called train, and it is going to train, we set the model in training mode. We move it to the device or the GPU. We set the running loss to be 0, number of correct predictions to be 0, number of training samples to be 0 to begin with, and then we go over the loader, right? And you can see here that it is loading the images and the labels. And an important thing here is that in every loop, when we load from the train loader, we are getting 32 images or whatever the batch size is. And before we do any work, we have to set the optimizer gradient to be 0. We have to clear the optimizer. That's what we are doing here. We are doing a forward pass on the images, getting the outputs, and this model is doing the forward pass of all images in the batch in one shot. Then we do a cross entropy loss, and we are calculating the loss. We are doing a back propagation, and then once we have done the back propagation, we get the gradients, and then we can update the weights using this optimizer. Then we are just keeping track of what is our total loss, updating the running loss, and then we are trying to figure out, what are the predicted class labels here. Taking the maximum of whatever the label has been predicted will give us the predicted label. Then we are updating the total number of samples that have been used and the correct number of predictions, right? We are updating that also. So whenever it is true that the predicted label is the same as the ground truth label, we are updating this number. So this will be used for calculating the training accuracy. As you can see here, the total number of samples and the correct predictions, it gives us the accuracy. We are also calculating the average loss. So this is the running loss divided by the number of elements. And then we are basically returning the average loss as well as the training accuracy. Next, we do the same thing for the validation. The only difference is that during the validation phase, we want to set it in evaluation mode and then send the model to the device, set the running loss, etc. the same way. And the one thing, this loop will also look exactly the same. The only difference is that we have to set torch.nograd. This ensures that gradient computation doesn't happen, and this eval mode ensures that the dropout and batch normalization, etc., they work the right way for evaluation. So again, this code is exactly the same as the training code. We get the validation loss, we get the validation accuracy, and we are all set. Now in the main function, we are basically, it takes in the model, the training loader and the validation loader, and we will basically create the history in this, the history of all the accuracy, as well as, the training accuracy, as well as the validation accuracy, and then we'll use that information to plot. So we start with training and validation losses. They are empty. Training accuracies and validation accuracies, they are also empty. These are empty lists. And then we say the best value, validation accuracy, and the best weights, because based on the best weights, we are going to save that weight. Okay, so now we are going over the entire training set for a certain number of times, right? And that number of times is called epoch. And epoch is the number of times we go over the entire training set. So based on the number of epochs, we are going to, let's say, I think the number of epochs is set for 20 in this notebook. So we are going to go over the entire training set 20 times and see what the accuracy we get, okay? So we get this train loss and train accuracy by calling the train function. We get the validation loss and the validation accuracy by calling the validation function. And we are going to append this information to training losses as well as validation losses accuracies. These are the things that we are going to use for plotting. So the summary writer is also used here, and we are basically putting training loss, validation loss, etc. under these in these directories, right? So you can look at the log files also. Now, if the validation accuracy is better than the best validation accuracy, in that case, we want to save the model, right? So we basically say the best validation accuracy is the validation accuracy. We update the weights. These are the best weights. And then, we save the model as well. That is it. And then we return the training loss, training accuracies, validation loss, validation accuracies. And you can see here, this function is being called, and you can see all these numbers update. You can see we are updating the validation loss, validation accuracy, the training loss, and the training accuracy for every step. Okay, now this we simply want to plot these with respect to time, with respect to the number of epochs. And you can see here, as the number of epochs increases, the training loss is coming down, which is great. The validation loss is also coming down, which is also great. Usually the validation loss, if you make it run much longer, this thing will switch. The training loss will come down to almost much lower number compared to the validation loss. So validation set, because the model has not seen the images in the validation set, validation loss is usually higher than the training loss. In the initial phase, the validation loss can be lower. The reason is that we have made the training extremely difficult, right? We are using dropout, which means that sometimes 40% of the times the neurons are not being used. And then, so it's a crippled network. That is one reason. The second reason is that we are also giving it more difficult examples, right? We are doing all these augmentations, which make the training set more difficult than the validation set. And that is why once you have trained it on this network, the validation becomes easier. But in the long run, you will see that the validation accuracy tends to be slightly higher than when you have trained it properly than the training loss. And this is because, the training data, the model has seen the training data. So it's getting better on the training data, but the validation loss, the validation data it has never seen, so it's higher. So that's the same story goes with accuracy as well. And you can see that we got in this may not be the right one. Every run you'll see a different accuracy number. And in our run, the last accuracy, the validation accuracy was in the 97%, and the training accuracy was in the 95%. When you get this notebook, run this for, let's say, 50 epochs, and you'll start seeing the difference. The validation accuracy may actually be higher. Usually it is higher. All right, so now we are all ready. We are going to save the model, and this is in Pytorch format. We are going to load the best model that we have saved during this iteration. Now keep in mind that this is an iterative process, so it's not guaranteed that the best model is always the last model, right? Generally, that may be true, but we want to keep track of whatever the best model was, because we may actually not get the best model in the end. It could be somewhere in between. So we load the best model, we set it to evaluation mode, and then we can use this model for any new image, right? So we write this function for prediction. This basically gets the model, and then we apply it to the validation set. So again, the code is very similar. We set the model to evaluation mode, send it to the device. Again, we have all the images and the labels. They are all empty in the beginning. All the predictions are empty in the beginning. The probabilities are empty in the beginning. And we load the image from the validation loader, right? And then we give the output. We get the output by doing a forward pass. And before we do that, we have to set the inference. We have to disable gradient, and you can call it inference mode, or also there is another way to do it is, as we have seen before, no grad is also an option. So now we are ready to, where is the code? Okay. here. And then, we get the probability and the output. We run it because the output is the raw output. It is not normalized to probabilities. When we run it through softmax, we get the correct output probabilities, and then we take the maximum, right? We get the maximum, and we also get the maximum probability. Then we move the image back to the CPU and move the labels back to the CPU. Everything moves back to the CPU, and then we return this structure. Convert it to NumPy and return this structure. One of the things to keep in mind is that these images we also need to denormalize the images. We have removed the mean and standard deviation. When we get the output, right, we want to make sure that for display purposes, we are adding the mean, first multiplying it by the standard deviation and adding the mean. And if the image goes out of range from 0 to 1, we clip it. Sometimes because of numerical errors, they could be slightly higher or slightly lower. And now we have the code finally for visualizing the prediction. Again, it's a very simple, you have sample images, ground truth, predicted indices, and then predicted probabilities, and the number of images that we want to display. So you go over this, you create a figure, you randomly get some samples, and then you get the outputs for those images. You denormalize the images, and then you use plotting, standard plotting to plot this. And you can see when we use these predictions, these are sample images, and the probabilities, you can see that they are pretty good. It says with one probability that this is a bald uakari. Now, I don't know what is a bald uakari, but this looks pretty bald to me. So we'll go with that. We know that these results are right because we can see that the ground truth, it says bald uakari as well. And the ground truth here also, it matches the prediction, as you can see in this label. So we are all good. As always, we also create this confusion matrix, and we have done this a few times. So I'm not going to go over this code. Basically, in a confusion matrix, I'm still going over the code. Basically, while creating the confusion matrix, we say what is the true value, right? So in the true value, we send in the ground truth labels, and what is the predicted value. And here we send in the predictions. Once we have done that, we are able to, we put a heat map so that this image gets colored properly. And then we plot this matrix. And you can see here that it does pretty good. Occasionally there are some off-diagonal elements every once in a while, but most of the weight is in the diagonal, which means that the prediction and the target, they are the same, right? Occasionally there is a misprediction. This predicted class, it says that it is 1 here, it is 8 here, but actually it is 0, right? And it happens for only one image, so not too bad. All right, so that is all that we wanted to cover in this fine-tuning notebook. So I hope that you learned a few things in this 2 series of notebooks about transfer learning and fine-tuning and how they are different and how it is done using Pytorch. That's all we wanted to cover in this notebook. Thank you so much.